The purpose of this short video is to help us play with vectors and finding out how to determine the angle between two vectors. And you are going to create your own applet. So it's a bit exciting. And we will use this applet later in the course. And you can come back to it whenever you want. So to begin with, from our home page, please click on the GeoGebra link. And that will take us to the GeoGebra main page. Make sure you're logged in, and so you would see here your identification. And what we are doing next is scrolling down a little bit in this main page, and we are looking for the geometry app. There's all kinds of very interesting apps. Today we're gonna play just with the geometry app. Once you click on this, you get a very clean interface. You will get basically a blank canvas and a series of tools on the left side. So we're going to keep this very, very simple. Follow along. One very important thing about GeoGebra is that the last tool you have used stays in the memory. So unless you want to do something else, you keep doing the same thing. But normally we do something and we want to go back to move. So keep these in mind as we progress. So what we are going to create is two vectors, and then we're going to find the angle between them. That's really a very simple task. So in basic tools, we're going to open this section which says more. And there's all kinds of objects here that you can edit or construct or measure. And there's different variety of lines. And as we come to lines, you will notice there's segments, lines, rays, and vectors, which is what we want. So whenever you use GeoGebra in this format, all you have to do is click on the option, and GeoGebra gives you a hint. It gives us select starting point and then end point. So that's what we're going to do. We're going to select a starting point and an end point, and we have created our first vector. Pretty good. And the vector goes from A to B. We're going to create another vector, so we're going to keep the same tool, and we're going to create a different vector now at a bit of a different angle, something like this. Very good. Now we are going to come here and click on the Move tool so that we stop creating vectors. Now, this allows us to move our vectors. So we have this vector that we can move in any direction. We can change the terminal point. We can change the initial point. So that's pretty good. So what we're going to do next is to measure the angle between these two vectors. We need to make sure that their initial points match. We use that term, or we use the other terminology that is, we have the arrowheads at the end, and the beginning of the vector we call the tail. So when we measure the angle between the vectors, they both have to have the same starting point, or they can be measured what we say tail to tail. So I'm going to make this vector and move it so that the ends match. If you notice here, we have now the vectors with the same starting point. And I can move these little points here that were the initial points of the two vectors. Very well. Now I'm going to measure the angle between two vectors. So the first part that is critical is that the vectors must be tail to tail, or the initial point is the same. So now we're going to come back here to our tools. And if you notice here, we have measurement tools, and we want to measure the angle. So when we click on angle, we will see that the instruction is for us to select 3 points or 2 lines. So in our case, we're going to select the points B, then A, and then D, and that will create the angle that we're looking for. B, then click A, and then D. And you will see right away that the angle appears. Let's go to the Move tool. We can move this value a little bit. And there's the angle between our two vectors. And of course, this is dynamic software. So as soon as we move it, the angle is updated. So we created our two vectors. We have now find out the angle between them when we place them tail to tail. And that was the main goal of our first little investigation. We'll do something more in subsequent activities. For now, we can explore a couple of more things. I can click on one of my vectors, and then I have a little menu that appears here. Let's say I want to change the color, make this one blue, and then I want to come to the other vector and make it red. I can also add a label for my vector. The label exists by default in GeoGebra. We don't show them at first, but we can choose to show them. So if we click on Show Label, we see that this vector is labeled as vector U. And similarly, if we come here and show the label for this vector, is called vector V. And now we have a very nice construction of our two vectors, U and V, that make this angle of 51.5 degrees. Excellent. So that's it for today. We are going to later find out how to add these vectors, play with them. So what I need you to do next is come to GeoGebra hamburger menu and save this construction. So save it perhaps as vectors 1. You don't need to share it. You can make it private or you can share it. It doesn't really matter. And save it. So now you have these and you can come back to it whenever we want. Thanks for watching. That is the summative activity for Module 1. And this is about climate change. So we'll go screen by screen. Hopefully this will clarify and help you better navigate Desmos activities because there are quite a few in this course. Here's the first screen that you have seen before. It describes you the purpose of the activity, and there's a link here that you can follow. So whenever you see a link, you can click on it and it will take you to a different place. The navigation, you can go here for the next slide. This tells you there are 17 slides. So or screens. You go to the next screen. This is screen 2. Here, there's a video that you can activate just by clicking on this little triangle, this arrow, and it walks you through the process of creating a regression in Desmos. I hope you have watched this because that will be critical for later screens. Then we have the first screen that has data, and you can see the data here is given to you. This refers to the annual global temperatures for the last 100 years in degrees Celsius, and it has data from 1919 to 2019. So all this data has been already plotted, and it suggests a certain shape. You can see that the axes are labeled. The x-axis indicates the years after 1919, the y-axis, the temperatures in degrees Celsius. And I can hide this panel or open it up by clicking on this section here, this little double arrow that you see. We usually have it open. Then the other item that you may want to explore, not in this screen, but in general, you can do it on any Desmos screen. Here, you can change the graph settings. So here we can have a number of graph settings that we can change. In this case, the screen is set up, so there's no need to change anything. But just for illustration purposes, I'm going to change the setting for the y-axis. So here you can see the x-axis, the minimum value is from -3 to maximum 108 on the bottom, and the y-axis from -2 to +25 vertically. So I'm going to change the y-axis from -2 to -20 instead of 25. So all I have to do is change the value here, and I can see what is the graph now that I've changed that setting. It's a bit more, it just shows me up to 20 degrees on the y-axis. I can change how the increments of the graph here by changing the step or leaving it blank. If I leave it blank, Desmos would do it automatically. Otherwise, I can change these. For example, the step on the y-axis, each little space is 0.25, a quarter of a number. Okay. On screen 4, then we wanted to gather your initial observations about the trend that you may see here. And if you notice, there may be a little bit of an upward trend for this data. You already provided answers for this, which is great. Then there's another video here, same stuff. You can just click on the arrow here and it will show you the video, or and this gives you the source. And this is about the impact of a change of 1 degree Celsius. On screen 6, we invite your reflections. So here you've done this already. You can come here and type. Um, uh, you can just type like you would normally. Just as an added reference, when you type here, when you click on this icon where it says type math, you can literally type operations with math. For example, if I wanted to type 1/2, I can just do 1 and then the divide sign, which is the slash that is on your question mark key on your keyboard. X square, for example, I would type X. To type the square, I would do the shift 6 and the 2, and etc. So then you would share with class. Now we're going to go to screen 7. Here is where I think there was a bit of a challenge. And I think critically, one of the problems here was that you may not have realized how to make a regression. So I need you to please follow up. I'm going to show you the first and second models, and then I believe you will be able to easily do the third one. Here's this, again, the data plotted. The scales are a little bit different. We can move the scales a little bit higher if we want to. Look at the scales. So we could actually move these to show the 0, but we deliberately left it up here to allow us to see the trend amplified. Okay, so here, each of these arrows indicate a folder. And inside each folder, there are questions and activities. So let's read the instruction here. Fitted data scatter plot, average global temperatures in 1919. Notice how the plot had changed. Observe the scales on the axis that we discussed before. Create 3 regression models to fit the data. Remember to use this is not the ampersand, the tilde. I'll show you where the tilde is in a moment. And variables y1 and x1 each time. If necessary, refer to the video on screen 2. This was explained in detail in screen 2, but it's just a reminder here. So to open the folder or close the folder, we click on the arrow. Now it's open, now it's closed. Right now, all we're going to do is create a model that is a linear model, which is y equals mx plus b. But because we're doing a regression, this is how we type it. We type y1, and then we are going to do a regression. It's not an equation because we're estimating it. So if you look on your computer keyboard, next to the left of the number 1, you will see the upper key that has 2 symbols. The uppercase symbol is called a tilde. And if you press on shift and that symbol, you will get that little, you can think, reverse S, horizontal. It's called a tilde. And so we're telling Desmos that we're doing a regression. So y1 regressed as a linear function. And so our linear parameters are m and b, m the slope and b the y-intercept. So we're going to type m and then x1, because that will take the data that we gave at the beginning. X1 plus b plus b. That's it. That's all we had to do. So if you notice, you can see that now we have created a linear model that more or less is a line of best fit, a linear line of best fit for the data that we had. So that's really all that it was necessary to do here. type it in this fashion: y1 tilde mx1 plus b. And this was explained in the video on screen too. So there's the model that you can see. And here we have the statistics. How spread is the data? I'm not going to go into great detail about this, but I will mention to you that R is the regression coefficient. R square is the square of this number, and the closest the R square value is to 1, that means we have a highest correlation. In this case, the correlation is 0.8036. Is not a bad model, but perhaps there's a model that could do better. And we are given by the graphing calculator the parameters m and b. So basically, we created an equation, a model that gives us the behavior of these phenomena if it was a linear case. The rate of change, or the slope, is 0.0099849, excuse me, and the y-intercept is 3.59. So that would be the initial temperature, and the m, the slope or the rate of change. That was a linear model. So what we're going to do next is to create a quadratic model, thinking this function may behave, or exploring what if the function behaves like a quadratic model. I'm not going to delete these. I'm going to hide it. I'm just going to click here. And now the model is still there. It's just hidden. I can activate it or hide it. One thing to be very mindful of, and I think this might have been happening to you, is this. If you accidentally click here, you are going to delete this line. And that's what I believe has been happening. So to undo, you can come here and undo, and you recover the work that you had done. If you had lost a lot of work, then you can come here and click on reset. And when you reset, the screen will be reset to the original form. So that means we would lose the work that we have done prior. So if I reset now, my model has disappeared. Okay, so I'm going to type it again because it doesn't take a long time. Y1 and then regress as mx1 plus b. And that's my linear model. Very well. I'm going to hold a little bit, move my screen a little bit up, and that's the linear model. Now I'm going to hide these, and just to make it clear for me, and I'm going to open the next folder, which will be a quadratic model. And the equation suggested here is this quadratic equation, ax squared plus bx plus c. And I'm going to perform a regression just as I did previously with these parameters. So in this case, I'm going to do y1, and I'm going to do the tilde again, and I'm going to type a x1 and the square, which is the shift 6, that little hat symbol. And then when I put the 2, it gives me the square. Then I press the mouse one time, or the right arrow key to bring it down so it's not an exponent anymore, plus b x1, and then plus c. And now you can observe that we have a different type of line. We have a curve, we have a quadratic, a parabola. And so this model looks a bit different. It seems to follow the trend a bit better. And we can see the R square is a bit higher. Our linear model, our R square was 0.8036. Our quadratic model is 0.87. So it is a bit better. And the parameters A, B, and C are given to us here by the regression that Desmos determined. So I hope this clarifies for you how to create the regression. In the next, again, we can hide this and or show it. I'm going to hide these, and then these would be the cubic model. And this cubic model would be ax cubed plus bx squared plus cx plus d. So it would be the same process. Y1 and tilde, and then ax1 cube. So then I would do shift and the 6, which is that little hat symbol. I put 3 for cube. and I press the right arrow key so that now I am back on the um, first line, plus bx squared plus cx plus d. I'm not going to do that because I want to leave this for you as an exercise in your own page. So based on what you have seen on the previous two. And I believe these will help you clarify things. Very important again, do not click here because you are going to be deleting things, and sometimes it happens accidentally. If that happens, don't panic. You can always undo. Okay. Well, so now you would have created three models. Um, and here, this screen gives you a picture of the models that we had before. As you already noted in your work, the best model was the cubic. And when we click submit, we get a bit of feedback. This is the model that had the highest R squared. You will verify that once you complete the model on screen 7, and you will analyze how the R square for the cubic is higher than it was for the square or for the linear. So I'm just opening and closing these folders to illustrate this. Um, Okay, then on screen 8, or screen 9, excuse me, you have a number of questions. And every time you submit questions, you are given feedback after you submit. I provided you feedback on this screen, and I believe you saw it and reacted to it and picked the correct options. Each screen, of course, is connected to every screen prior. So you are building gradually on this activity and most of the Desmos activities. Then on screen 10, you enter the values, and I know you have done that correctly. And same thing on screen 11. And you're getting feedback immediately here by getting a tick mark when the value is correct. Then there's another video that contextualizes that the importance of the average rate of change, although the values are very small, the cumulative impact is very significant. So I encourage you to see the video if you haven't. And then now we ended up with this model, right? Of course, the numbers are very different because it's really a model that is based on actual numbers. So the numbers, if you notice here, the leading coefficient for the cubic term is very small, is in the order of 10 to the power of -6, and so on and so forth. And then here, we are want to use our model to predict. So we're going to extrapolate. So I'm going to read this screen, at least from the beginning, from this section. Extrapolation is a term that refers to extending inputs in an equation to forecast values beyond the existing data set. To extrapolate, we evaluate the valuations at values beyond 2019. So we are assuming we're at 2019, and we're looking what if these trends continue. So here, I believe you already identified this correctly. We have to evaluate the function that we have here, t of t, t being the year after 1919, with t of 0 being 1919. So t of 1 would be the temperature in 1920, t of 10 would be the temperature in 1929, and so on and so forth. So here, which of the following shows what we want to do? We need to evaluate when the value is 106. So that means 106 years after 1919. And we give feedback when we supply the answer, and that's correct. So we proceed to the next screen. By the way, if we answer these incorrectly, our feedback tells us that the correct extrapolation is among the other answers. Please review. So one of the biggest small but big challenges that we have on these activities is to take our time to really read the feedback and to read the instructions. Sometimes we're used to glancing or reading very quickly, and sometimes in math that doesn't help us because we need to be very thorough in our reading. Next, we go to the models that we have already. So here, let's read the instructions. How much time is left? If these trends continue, when will the global temperature increased by 1.5 degrees from the beginning of this century. So click on the circle next to the equation to show the graph, and then open each folder sequentially. So here it is. We're going to have our model. We have chosen the cubic model so we can see what is happening, which would be very worrisome if it were to continue. The temperature in the year 2000. So I'm going to open this folder, and we're going to follow the instruction here. Desmos will evaluate the function for any value of t, meaning the years, based on your input. For instance, for the year 1949, t equals 40. We type t of 40. So we don't have to do the math outside and evaluate for t of 40 and substitute in this equation. We're going to use the graphing calculator to do that. So all we literally have to do is type t bracket 40. And you will see that Desmos gives you the value. So in other words, the temperature in the year 1949, based on this model, was 13.9 degrees. So I hope you can see this. I think in this screen, you accidentally erased a lot of the things by accidentally clicking on the X. And that's why in your observation, what was happening is the things were disappearing. They only disappear when you delete them. So please do not click on these X's because that's what will happen. So now you have to figure out what is the year 2000. And let's determine that. So it would be t of the year 2000. So the year 2000, we would figure 2000 minus 1919, right? And that can be done easily. We actually have a calculator here if you want to access it. So we can even do this, 2000 here in the calculator minus 1919, and that would be 81. I can open the calculator or I can close it here, and it's available to you anytime by activating this little icon and closing it. So now we would evaluate T of 81, and that is our temperature for the year 2000, which is almost half a degree more than in 1949. And then we have a folder here that helps us check in. So when we click here, it tells me, did you determine T of 81, which is exactly what we did. So this is just a check-in to make sure that we were on the right track. If not, please review. And it gives us the answer, really. The temperature should be 14.3752 degrees and is rounded. So basically, this little folder where it says check-in is only to help us make sure that we're on the right track. And that's the functionality of Desmos. I can go to my next folder, and these folders I can leave open or I can leave closed, whatever I prefer. And then what is 1.5 degrees from the year 2000? And now we're going to place the point for the year 2000 on the graph. So we're going to type a point on the graph, and we literally type the 81 and T of 81. This is the function notation. So we'll see what happens. So we're going to open a bracket. We're going to type 81, comma, capital T, because that's our function, T of 81. And you will see that there's a point appearing on our graph. You notice here that is there. We can actually put a label. If we click on label, and that gives us the point. So basically in the year 2000, which is 81 years after 1919, the temperature is predicted to be 14 degrees and 3.75 thousandths of a degree. So that is another tool you can use. If you notice, we really haven't done a lot of calculations, paper and pencil, because we have the model and the Desmos calculator that does that. We're less interested in this activity in doing the calculations and more interested in interpreting what we're getting, and also becoming more familiar with the Desmos. And here there's a note, as we have seen, T81, the temperature in the year 81, is the temperature in the year 2000, T equals 81. we are interested in this temperature increasing by 1.5 degrees. So we can type an equation to help us see this temperature in our graph. And it's going to be this: type y equals T of 81, which was the temperature we have, plus 1.5 in the space below. And that is exactly what we're going to do. Y equals the temperature here, 81, plus 1.5 degrees. There it is. And if you notice now, what we have done is you created another function that is a horizontal line that is at 15.875. So this is the line that tells me uh, the temperature would be 1.5 degrees higher than the year 2000. And now we can find, if we observe the graph, you'll notice the intersection. Desmos gives you the point. So you can see here that it gives us a point that is, if you hover over the point, it tells you the coordinates. The x value, or the years, is 122.073, and the temperature is 15.875. So you can see that 122 years after 1919, the temperature is 15.875, etc. So now you can leave this open. You can close it. There's a second check in here, and it exactly tells us to verify what we did. You should see a horizontal line at y equals 15.875, which is what we have. If not, please review. So these check-ins are built in as feedback for you. I think the key issue or the biggest challenge that you had was this erasing accidentally of the information. So that, of course, created a lot of confusion and didn't allow you to complete the activities the way they were intended. I hope this is helpful, and I hope will clarify things for you. The navigation on Desmos activity is very much like this. So I'm going to leave this like this for you to. You may need to reset, and remember, resetting the screen, you would need to do this and then reset. But I hope the video. I'm not going to reset because there's no need for this now. This video helps you clarify these things. And of course, then you can continue and finish the activity, which I believe you have done. So I hope this is helpful. Please, I'm going to probably make another short video to show you how to use. You have already used our communication in the e-class at York, the private messaging, but I know it also was challenging you a little bit. So for now, you can send me emails if you want, but if you get familiar with the private chat, it might be helpful. I hope this is useful. Thank you for listening.